We spend our entire lives online now. We click links, send emails, stream video, and it all just feels, well, instantaneous.
Completely. It's like magic.
Yeah, exactly like magic. You tap a piece of glass here in London, and a server somewhere in California just wakes up. But have you ever stopped to think about the invisible decision that makes that happen?
It's one of those things we totally take for granted until, it breaks.
Right. The Wi-Fi drops, and suddenly everyone's a network engineer.
Mm-hmm.
But here's the thing that really stuck with me from the research. Every single time you move a piece of data, and we're talking microseconds here, there's a physical box somewhere making a rigid, logical choice.
It's not just flowing like water. It's being actively directed.
And that director is the network switch.
The switch. That's our subject.
And I know what some listeners might be thinking. Okay, a beige box with blinking lights.
Yeah.
How interesting can this really be?
Right. But the source material we looked at calls it a traffic director, and that's the perfect way to think about it.
So it's not just a fancy power strip for the internet.
No, not at all. If the internet is a highway, a router is like the GPS planning the long trip.
Right.
But the switch is the traffic cop at every single intersection, actually waving the cars through.
Without it, it's just chaos, a total pileup.
Exactly.
Okay, so here is our mission for this deep dive. We're going to shrink you, our listener, down to the size of an electron.
We're jumping into the wire.
We're going to trace the journey of a single data frame from the moment it enters the switch, what the pros call ingress,
to the moment it leaves, or egress, and we're going to look at the brain that makes it all possible.
We've got some great material here on the hardware, the memory tables, the logic loops.
And even a little battle between speed and perfectionism later on.
Let's start with the box itself. It looks so passive, right? Is it really doing all that much? Or is it just a kind of smart extension cord?
Visually, it's boring, I'll give you that. But the sources, they call it the anatomy of a decision. And inside, it's a hive of activity. It's definitely not just wires connecting pin 1 to pin 1.
Because if it was, my email would go to everyone in the building.
Which would be a massive privacy nightmare. So inside the box, you have buffers, forwarding engines, and these really specialized chips. And this is where we have to get technical for a second. The sources make a big deal about something called an ASIC.
ASIC, Application-Specific Integrated Circuit. Now, I have a powerful laptop right here. Top-of-the-line CPU. Why can't a switch just use a normal processor like that?
It really comes down to a generalist versus a specialist. A CPU, like in your laptop, is incredible because it's flexible. It can run spreadsheets, games, a web browser.
It does everything.
But that flexibility has a cost, and that cost is interrupts.
Interrupts?
Yeah. Your CPU is constantly stopping what it's doing to handle something else. The mouse moves, that's an interrupt. An email comes in, interrupt. It's constantly context switching.
And I'm guessing that's bad for network traffic.
It's a disaster. The data would literally pile up. It would degrade. An ASIC is different. It's hardware that is hard-coded to do one thing and one thing only.
Which is?
Switch network frames. Think of a CPU as a master chef. He can chop, bake, fry, but he has to stop chopping to check the oven. An ASIC is like a factory robot that only chops carrots.
It could make a souffle.
It would destroy a souffle, but it can chop 1,000,000 carrots a second because the logic is physically etched into the silicon. It's not software.
So when the notes talk about wire speed, that's what they mean.
That's the goal. The ASIC uses parallel processing. It handles gigabits of data across dozens of ports at the same time. It doesn't get interrupted because it doesn't have an OS in that sense. It just moves electrons.
So the ASIC is the muscle, the robot, but you still need a brain to tell the muscle what to do. The notes say the switch is a bridge between the physical and the digital. And
that's a really key concept. You have the physical world, the literal ports on the front of the box, port 1, port 2, and so on.
And then you have the digital world.
Which is the MA addresses of all your devices.
Right, the MAC address. I think people see those long hexadecimal codes and their eyes just glaze over. It's basically just a serial number, isn't it?
It is, but it's a structured one. 48 bits. The first half tells you who made the device, Apple, Dell, Cisco. The second half is the unique number for that specific network card.
Like a VIN number on a car.
Exactly like that. Every single thing on the network has one. Your laptop, your printer, your smart fridge. And the switch's job is to build a map that links the physical port to that digital MHA address.
And that map, that brain, is the CAM table.
Right. CAM. It stands for Content Addressable Memory. It's the master switching table.
I've heard of RAM, random access memory. Is a CAM different?
It's not just faster, it works backwards. This is a really cool concept.
Right.
In normal RAM, your computer asks, go to address row 4 and tell me what data is there.
Address leads to data. Got it.
Right. But in networking, we already have the data, the MC address. We need to find the address, the port number. If we used RAM, the switch would have to search every row, one by one. Is this the MC? No. Is this one? It's way too slow.
Yeah, with thousands of devices, that search would take forever.
Exactly. CAM flips it completely. The switch presents the data, where is this MNC address? And the memory instantly returns the address. It's on port 4.
In a single clock cycle.
One clock cycle. It's like a hardware search engine.
Which explains why enterprise switches are so expensive that memory can't be cheap.
It's very expensive, draws a lot of power. But it's the only way you get that wire speed performance we were talking about.
Okay, so we have this super fast lookup table. But here's the catch, and this is where the logic gets really cool. The switch doesn't come with this list pre-installed, does it? The CAM table is empty when you plug it in.
Completely blank.
So how does it learn? Does it send out a ping to everyone and ask who they are?
Nope, it's actually much lazier than that. Learns passively. The source material calls this logic loop step 1, learning. And the trigger is the source MC address.
So this is the aha moment. The switch learns where devices are not by looking at where data is going, but by looking at where it came from.
It's like a party host standing at the door. When you walk in, they write down your name and which door you use. They don't know where you're going to sit yet, but they know how you got in.
Okay, so my little electron-sized data frame enters the switch, ingress. The switch stops it and looks at the source MIC address. And then it asks its CAM table, do I know this guy?
And there are 3 specific paths here. Path 1, it's a new device. The source MAC is not in the table. The switch just makes a note. It writes down that MAC address and the port number it came in on. Done. Learned.
Okay, path 2 is a known device.
Yeah.
The MIC is already in the table on that same port.
In that case, it just refreshes a timer. The sources mention a 300-second or 5-minute timer. Switches have short memories. If they don't hear from a device in 5 minutes, they forget it to save space. So if you send something, it just resets your timer. Okay, he's still there.
And path 3, what if I move? I unplug my laptop in my office, and I run down the hall to a conference room and plug in there.
So that's a moved device. The switch sees your MSC address, which it knows, but suddenly it's coming from a different port. It just goes, oh, you moved, updates the table with the new port, and resets the timer.
That's pretty clever. So all of this learning and timer resetting happens at ingress.
All at ingress. Before the switch even thinks about where the data needs to go, it takes that split second to learn from where it came.
Okay, so now the switch knows who sent the data. Step 1 is done. Now for logic loop step 2, forwarding. This is where the traffic director actually directs.
Right. Now the switch finally looks at the destination MC address and asks, where do you want to go?
And we have 3 scenarios again. The first one is known unicast.
This is the ideal situation. The destination address is in the CAM table. The switch looks at its map and sees, oh, that device is on port 12.
So it sends the data directly out of port 12.
And only port 12. No other port on the switch even knows that conversation happened. It's clean, it's efficient, it's private.
But what if the data is meant for everyone? A broadcast?
Yeah, sometimes a computer needs to shout. Maybe it's asking, is there a printer on this network? In that case, the destination address is all Fs, FF, 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 everyone.
Code for everyone.
Exactly. The switch sees that and it floods the frame. It makes a copy and sends it out of every single port.
Except one.
Yes, except the ingress port.
And this is the golden rule, right? The source was very clear on this. Frames never exit the ingress port. Why is that so important?
It's all about loop prevention. Imagine you have a couple switches connected together in a circle. If you send out a broadcast and a switch sends it back the way it came in,
You would just go around and around forever.
and it would multiply. It's like audio feedback from a microphone, but for data. They call it a broadcast storm, and it can literally melt a network. It'll consume 100% of the bandwidth. That one simple rule is the first line of defense.
Okay, that makes total sense. So the third scenario, unknown unicast. I'm sending something to Bob, but the switch has never heard from Bob before.
Right. The destination is specific, but the CAM table is blank for that address. The switch can't just throw it away. That would be data loss. So what does it do?
It has to guess.
It treats it like a broadcast. It floods the frame out of every port again, except the one it came in on, just hoping that Bob is out there somewhere to receive it.
So for a split second, it dumbs itself down and acts like an old school hub.
Exactly. It shouts, I don't know where this goes, so I'm giving it to everyone. It relies on the fact that only Bob's network card will actually accept it. Everyone else will see it's not for them and just drop it.
Let's make this really concrete. The source has this switch it scenario that I think nails it.
Let's walk through it.
Okay, so a brand new frame enters port F1. The source MEC ends in 1111. The destination MEC ends in 3333.
Okay, stop right there. Frame it's the wire. First step, learning. The switch sees a frame coming in on F1. It reads the source, 1111.
The table is empty, so it adds 1111 is on F1 to its CAM table.
Done. It now knows where you are. Now for step 2, forwarding. It looks in the destination, 3333.
It checks the table again, but the table only has one entry. It has no idea where 3333 lives.
So that's an unknown unicast.
Which means it floods.
It floods. The switch copies that frame and sends it out of port 2, port 3, port 4, every port except port 1.
Now, here's where the magic happens. Let's say the device with MAC 3333 is on port 3. It gets the message, and it replies.
And this closes the loop. When 3333 replies, its address is now the source address. The switch sees this new frame coming in on port 3. What does it do?
It learns. It sees source 3333 on port 3 and adds that to the list.
Precisely. So the next time 1111 wants to talk to 3333, the switch checks the table, sees both addresses, and it creates a direct private connection between port 1 and port 3. The shouting is over.
That is just so satisfying. It's a self-learning system.
It really is. But there's one more layer here. We know how it decides, but when does it decide? There's a physical reality here. The source talks about 2 different methodologies, the perfectionist versus the speedster.
The classic engineering trade-off. Let's start with method 1, store and forward. This is the perfectionist.
This is what most networks use, your office, your home. In store and forward, the switch is cautious. When a frame starts arriving, it waits. It buffers the entire thing.
And frames can be thousands of bytes long. That takes actual time.
It does. It's called serialization delay. Imagine a train entering a station. The station master waits for the very last car, the caboose, to get onto the platform before he lets the engine leave for the next stop.
Why wait?
Because at the very end of the frame, in that caboose, there's a mathematical checksum, a CRC.
The seal of authenticity.
Basically, yeah. The switch does the math on the whole frame it received. If the numbers don't match the checksum, it means the data got corrupted on the wire. A bad cable, electrical noise, whatever. The perfectionist switch says, this is garbage, and just throws it away.
So it guarantees data integrity, but the downside is latency, that waiting.
Exactly. Which brings us to method 2, cut-through switching, the speedster.
This is for when microseconds are everything.
Everything. In cut-through, the switch does not wait for the caboose. It reads just the first few bytes, just enough to see the destination M table.
So as soon as the ASIC finds the destination port in the CAM table,
the gate is open. The front of the frame, the engine, is already leaving the egress port, while the back of the frame, the caboose, is still coming in the ingress port.
Wow, it's in 2 places at once. That sounds incredibly fast.
It is. You can lower latency from, say, 100 microseconds down to maybe 3 or 4.
But who needs that? My Netflix seems to load just fine.
You don't need it for Netflix. You need it for high-frequency stock trading. If your algorithm's buy order gets to the exchange 10 microseconds after the other guys, you lose millions. They don't care about the occasional error. They care about being first.
But there's a huge risk, right? If it sends the engine before it sees the caboose.
It never sees the checksum. It has no idea if the frame is corrupted. It will happily forward garbage data all over the network.
It's the shoot first, ask questions later approach.
It absolutely is. The source mentions a middle ground, fragment-free, where it waits for the first 64 bytes to at least avoid forwarding obvious collision fragments, but really, the 2 main camps are store and forward and cut through.
It's just amazing that we have different hardware logic for different needs. One for reliability in an office, one for pure speed in a supercomputer.
It all comes back to the application.
So let's zoom out. We've been on Electron, we've traveled through the buffers, we've seen the ASICs fire. What's the big takeaway?
For me, it's that the internet isn't a cloud. That word makes it sound so fluffy and intangible. It's not. It's rigid, physical boxes running high-speed logic, making billions of decisions a second based on lists and timers.
And what stuck with me is that it's listener first. The switch literally can't do its main job directing traffic until it first shuts up and listens to where everyone is coming from.
That's a great way to put it. It listens at ingress to direct at egress.
I want to leave our listeners with one final thought. We talked about flooding. When the switch doesn't know something, its default action is to shout. to send it to everyone.
The unknown unicast. Unnecessary evil.
It is. But think about the sheer scale of the internet. Billions of devices. At any given second, how much of the traffic flying around the globe is just our own infrastructure shouting into the void, "Who are you?" just because it hasn't learned an address yet.
That is a staggering thought. The constant underlying noise floor of the internet.
And the only reason it all works
Is because those ASICs we talked about are fast enough to filter out all that shouting before it ever hits your computer's CPU. If your laptop had to process every one of those shouts, it would just freeze solid.
So the ASIC is basically the noise-canceling headphone for the internet.
I like that. I'm definitely stealing that one.
Something to think about the next time you plug in a network cable. Thanks for joining us on this deep dive.
My pleasure.
We'll see you on the next one.